I'm Evan Barras from the University of New Mexico, and today I'll be presenting on my work on designing a quantum algorithm to simulate open quantum systems based on the quantum trajectories approach to open quantum systems. And this is joint work between me and my advisor. So let's jump in. Oh, oh, oh boy. Okay, let's see. There we go. Okay, we're back. So let's briefly review a bit about what an open quantum system is. Normally we're concerned with some quantum system, which can be described by a state acting on the bounded operators over some Hilbert space. But in the open quantum system paradigm, our quantum system is exposed to some environment. And so in order to model this, what we do is we tack on an additional Hilbert space that we call the environment. And then we basically model the thing as a closed quantum system on this joint system plus environment Hilbert space. And in general, for an arbitrary open quantum system, this joint system and environment system is evolving under some Hamiltonian, which can be broken up into a portion that acts on the system, portion that acts on the environment, as well as a portion that couples the system to the environment called the interaction term. And to recover our state of the quantum system, we simply just take the partial trace over the environment to recover our quantum state of the system. Oh man, okay. Sorry about that. Yeah, so the quantum systems, the open quantum systems we'll be concerned with for this talk are what people sometimes call Markovian open quantum systems. These are quantum systems that are weakly coupled to an environment where the environment resets quickly enough in order to sort of forget the information it learns about the system when interacting with it. These types of open quantum systems are governed by something called the Lindblad master equation, which can be broken up into two components, a component that looks like our good old familiar von Neumann equation here, and then also a component that models the dissipation due to the environment, which is generated by these operators that are called jump operators, and I denote with L over here. In general, Lindbladians are super useful. They've been used to model everything from environment-induced thermalization to decoherence in quantum systems. And the task we'll be concerned with today is something called Lindbladian simulation. So in the Lindbladian simulation task, we are given a input quantum state, requested simulation time, as well as a requested precision of simulation, as well as some sort of data about the type of system we're simulating or the specific Lindbladian. And the goal of this task is to produce some output state, rho out, which is approximately equal to the state that would be the true state if we just evolved rho 0 under the map given by the Lindbladian we're trying to simulate. The current state of classical algorithms for this problem are, they're known to be inefficient, and we don't really expect classical algorithms to be efficient for this in the general case due to hardness evidence. So with that in mind, let's consider designing quantum algorithms to solve this task. And so I've listed some common Lindbladian simulation algorithms here. This is not an expansive list, so if I didn't list your favorite, sorry about that. But in general, I would say the state-of-the-art Lindbladian simulation algorithms have a query complexity to your Lindbladian generator that is multiplicative between linear in time and polylog in time. And in general, this state-of-the-art query complexity is achieved by these two algorithms with the red star up here. And in general, the primitive gate cost for these algorithms scale similarly to the query costs here. So that means if we have a way to implement our input model, which gives our quantum computer access to the Lindbladian that we're trying to simulate, and that circuit is efficient, then that gives an overall Lindbladian simulation algorithm that is efficient. All of these algorithms essentially give algorithms that are efficient. And so for the algorithm that I'll be presenting today, we we will assume a block encoding access model for our Lombardian. Essentially what a block encoding is it's some unitary that, that acts on a system plus ancillary register. And if you post-select on the ancillary register being in the initial state, then you generate the action of the operator that you're trying to block encode on your system register. And so for our algorithm, we're going to assume that we have access to block encodings for the Lombardian's Hamiltonian, as well as each of the jump operators. And our main result is essentially listed here. So essentially for Lombardians with jump operators that satisfy this condition, then we construct a quantum algorithm that simulates this Lombardian that requires an additive many queries to each of these jump operator block encodings as well as its inverse, in addition to these other resource costs. But it's also important to note that for a purely dissipative Lombardian where we don't have a Hamiltonian, then we can further reduce our additional 1 and 2 qubit gate costs to also be additive between t and log 1 over epsilon. And this ends up actually being optimal for these types of Lombardians that satisfy this condition as well as don't have a Hamiltonian. And to see kind of how we do this, instead of simulating the full Lombardian master equation, we simulate realizations of the stochastic master equation given here, where this dn is a Poisson increment. And essentially what our algorithm does is in compilation, it samples one of these trajectories, which are a realization of this stochastic master equation. And then we just simply compile the quantum circuit, which approximates the dynamics of that trajectory. And then we know from the theory of quantum trajectories that essentially our measurement statistics for this protocol are equivalent to that of sampling from the actual state evolved under the solution to the Lombardian master equation. So to see kind of why we end up achieving the result that we did, if we revisit the stochastic master equation and then apply our algorithm's constraint of essentially the sum over your jump operators is proportional to the identity operator, then the stochastic master equation we get looks something like equation 4 right here. And what this equation describes is a physical process where you have periods of time where you're evolving deterministically under some Hamiltonian. And then you have random moments where you're applying this jump map, denoted J here. And these jump maps are driven by this Poisson increment, and so they occur with a Poisson clock. And it's the key feature about this process is when you apply one of these jump maps, it implies essentially a constant many queries to your jump operator. And so essentially what we do is the main technical content of our work is bounding the number of times you need to apply this jump map in order to reach a required precision for the simulation. And then once you get that, that tells you essentially how many queries you need to your block encoding of your jump operator. And that's kind of the basic picture. So other than that, if you want more information, you can check out our paper on the archive right here. And thanks for your time.